So we have question given a particle of mass m moving in a potential v as given, where omega naught and a are positive constants. Find angular frequency of small oscillation about stable minima point. Right. So suppose this potential function is of some form, and this is a rough graph. I don't know what the exact curve would be, so I'm drawing a rough graph. So if there is a point of stable minima, let us say this is point of stable minima, x naught, then if the particle is at this position, then if it is displaced slightly from this stable position, it will execute simple harmonic motion. And the question is to find the time period of that small oscillations. So first step in this question is to find the point of stable minima, which will be when the slope of v versus x graph is 0. That means del v over del x is 0. So del v over del x, this will be equal to half m omega naught square 2x plus minus 2a x to the power minus 3 2m, and this should be 0. So this implies that m omega naught square x is equal to a upon mx cube, implies that x to the power 4 is equal to a upon m square omega naught square, implies that point of stable minima, let us say that is x naught. So if I am taking it to be 0, then x naught will be equal to a upon m square omega naught square raised to the power 1 by 4. Now I do not know that whether this point of equilibrium, that is where f is 0, whether it is a point of minima, maxima or neutral equilibrium. So the test for that is, for point of stable minima, we know that del v by del x is equal to 0, and the second derivative should be greater than 0 because slope should be increasing, so that it is a stable point. So let us find del 2v by del x2, del 2v by del x2, and that will be differentiating this, we have m omega naught square, and differentiating this we have plus 3a upon m x to the power 4. And clearly, since x, this x point of this at x is equal to x naught, this is positive, this will be positive, so this will be greater than 0. So x naught, therefore x naught is a point of stable minima. X naught is a point of stable minima. Now the next step is to find the force. So what we need is that force at x naught plus delta x. That is, if the particle is displaced from x naught by a distance delta x, then at this position force should be proportional to delta x and directed towards x naught. So this should be proportional to delta x with a negative sign. So I need equation of this form. So what I need is function of x naught plus delta x is equal to minus some constant, some positive constant into delta x, into delta x. And then this k, this will be the effective SHM constant, and this will be equal to m omega square, where omega will be the angular frequency of vibration. Angular frequency of vibration. Omega will be the angular frequency of vibration. So this is what we need to do. So let us see what will be f. F will be equal to minus del v by del x. F will be equal to minus del v by del x. So this will be equal to minus m omega naught square x minus a upon mx cube. So this is force as a function of x. Now let us see what is force at x naught plus delta x. That is just a little bit away from the equilibrium position. So force at x naught plus delta x, this will be equal to minus m omega naught square x plus delta x minus a upon m x naught plus delta x is to the power 3. So this is what we need. This is what we need. So let us see now so this is the force that we have. Now force at x naught plus delta x, this is equal to minus m omega naught square x plus delta x. Now let us see what we can do. Is delta x is very small as compared to delta is small to in comparison to anything. Delta x will be small in comparison to any value. So x naught is much larger than delta x. So I will take x naught outside and then use binomial expansion. So I can write minus a upon m x naught cube. So this will be 1 plus delta x by x naught. So this will be 1 plus delta x by x naught raised to the power minus 3. Now I can use binomial expansion here. So this is minus m omega naught square x plus delta x, x naught plus delta x minus a upon mx naught cube 1 minus 3 delta x by x naught. 1 minus 3 delta x by x naught. So now I will open these brackets. So I have minus m omega naught square, sorry I keep making this mistake, x naught minus m omega naught square. So I think just a second, I think I have maybe made a mistake. Yeah, sorry, there is a mistake. What I have done is, since I was differentiating this will be 2x and there will be minus sign here. So this will be positive negative. When there is minus del v by del x, this will be negative, this will be positive. So there is a plus sign here, sorry, there is a plus sign here. So I have f is equal to, this is plus sign here. Right. So this is plus a upon mx naught cube and minus 3a delta x mx naught to the power 4. So let us see what this is. These two, if I separate these two, I have minus m omega naught square x naught plus a upon mx naught cube, and I have minus m omega naught square, sorry, there is m omega naught square delta x, m omega naught square delta x minus 3a delta x upon m x naught to the power 4. Now we can recognize that this term is 0. We can recognize that this term is 0 for x naught. See, we have m omega naught square x minus a upon mx cube 0. So this is where we started from. So this term is 0. which we had used earlier. So this term is 0, and now we have to see what this term is. So this term is equal to minus m omega naught cube, m omega naught square plus 3a upon m x naught to the power 4. Now let us see what is x naught to the power 4. X naught to the power 4 is a upon m square omega naught. So this is a upon m square omega naught square, and we have outside delta x. So I have equation minus 4m omega naught square delta x. So this quantity here is our SHM constant. So k is equal to 4m omega naught square. This is actually equal to m omega dash square, where omega dash is angular frequency, which is equal to 2 pi over time period, where t will be the time period of small oscillation. So I have simple answer, omega dash is equal to 2 omega naught, and I could not have expected such a simple answer from seeing such a difficult potential function. Also notice that it is not such that we can just neglect this potential function and take this potential function, because in that case, if this was the potential function, our omega would have been omega naught, but it is 2 omega naught. Our angular frequency would have been omega naught, because we know simple SHM potential function is half kx square. So if k is m omega naught square, angular frequency will be omega naught. But we are finding angular frequency to be 2 omega naught. It is totally different, right? So we cannot just neglect this potential function. We have to take this potential function. It is not so simple. We cannot just neglect this potential function and take this potential function, right? We have to follow these steps. So angular frequency we have found is 2 omega naught. So this will also be equal to 2 pi over time period. So time period will be equal to pi over omega naught. So our answer is angular frequency is equal to 2 omega naught and time period is equal to pi over omega naught.